of the fall semester. Today's speaker is Dr. Min-jae from University of Chicago. Uh, Actually, I first met Min-jae at APCTP workshop this May, last May, yeah.
Right.
And because I got the big interest from his talk, so I invited him to our secret seminar speaker today. I know he's studying mainly string field theory and also bootstrap. Today he will talk about bootstrap. Min-jae, please start.
Thank you very much. Thank you very much for the kind of warm introduction, and also for giving me the opportunity to speak here. I really wish I were able to visit Korea in person and give this seminar in person, but unfortunately there were some administrative issues that I had to deal with. So uh, this is the best, I guess. But I'm very happy that I can present this Zoom seminar today. So today I'm going to tell you about how to bootstrap physics at finite temperature. Okay? And this is mainly based on these works that I have been involved in during the past few years. And these are a list of my wonderful collaborators. And please stay tuned for this upcoming paper, which we hope to post on the archive sometime this month. And before jumping into physics, I would like to introduce you to a song. Okay. This is a song recommended to me by Igor Klebanov when I was organizing a workshop at Princeton named Positivity. And the name of the song is essentially The Positive. It's a pretty nice song. As you can see, it has more than 1 million views on YouTube. So it's gotta be a nice song. It has even better lyrics. So let me share some of the lyrics with you. So it says, you got to accentuate the positive. So these musicians know that positivity is something important. Eliminate the negative. So they know that if positivity is not obeyed, your physics is in danger. Okay? So you should eliminate such a thing. And then they're also talking about maximizing something and minimizing something. And if you actually have been exposed to some of the recent numerical bootstrap program, actually you'll see lots of the keywords that comes into play here. Okay? So today my goal is to tell you about how physicists would interpret these lyrics and actually realize them in some specific systems. So the first question we can ask is, where is positivity in physics? Okay? Say we have some observable O, and then we want to make some measurement. This could be in the context of either classical mechanics, quantum mechanics, stat-mech, or stochastic processes, whichever physical context you want to think about. And the resulting thing is something we interpret as the expectation value of this observable. And if it describes something in the real world, it better take real value. Okay? Well, on top of this, if there is some notion of this observable being positive, and if your measure is also positive, then it's fair to expect that the expectation value of such an observable is going to be also positive. If this sounds too abstract, let's directly jump into the first example. Okay? So this is a toy example. We are going to consider generically a function on a real line. Okay? Let's call it f of x. And we are going to define the corresponding expectation in the following manner. So if you wish, this is just 0 plus 0 dimensional phi-4 theory. And it's defined by this measure. And as you can see, this exponential factor is positive everywhere. So the measure is positive. So if you now consider expectation value of some function p, which is positive everywhere, of course, the corresponding expectation value is going to be positive. Okay. For example, if you take x squared expectation value, it better be positive. This actually implies that if you now confine your interest to the real polynomials, in particular, if you take some real polynomial square, the corresponding expectation value should be positive. And this is actually equivalently written as positivity of some matrix M. Okay. This matrix has elements I and j, which is expectation value of x to the I plus j power. Okay. So this positivity and this positivity are equivalent. Of course, this positivity holds for any positive measure which is not specifically required to be this one. So now we can ask, what are the conditions which specify this specific measure? That is the content of Schwinger-Dyson equations. As we are all familiar with in QFT, Schwinger-Dyson equation simply is a statement that if you have a total derivative and integrate it, then you get 0. Okay? Actually, once you just write this out, what you are going to end up with is this type of relations. This is relation between different expectation values of different monomials. So if you actually write this out and try to solve it, you will realize that there is only one independent variable left, which is the expectation value of the x squared. So now we can come up with the following problem. Okay, the problem is like the following. We want to either maximize or minimize x squared expectation value subject to this positivity condition, which is saying the measure is positive, and Schwinger-Dyson equation, which is coming from this specific measure we have. Actually, as you can see here, what this is going to be doing is basically explore the region constrained by this and this equation. And whenever you have this type of matrix positivity, such a program is actually called semi-definite program, SDP in short. This is a very well-known programming in convex optimization literature, and we are actually having such a problem here. So SDP is something very standard by now. So what do I mean by it being standard? What I mean is that it is so standard that there is actually a built-in function for semi-definite programming in Mathematica. Okay? So here's a very short code for dealing with this. So these are basically the expectation values. We are basically looking at the constraints on x squared expectation. And then this is basically imposing the Schwinger-Dyson equation. And I'm building a matrix which should be positive. Okay? And this cut 20 means that I'm going to consider monomials up to degree 20. Okay? Because we are now teaching our computer about this measure, we have to plug in only finite number of stuffs. So I'm going to just make the cutoff on the degree of the polynomials under consideration. And this min and max are basically the minimization and maximization procedure that I described before. Subject to all these constraints, we want to find either minimum or maximum of x squared. And this is a specific function which is implementing this job. And in less than a second, these are the numbers that you're going to obtain. Okay, this is the mean, this is the max. And as you can see, they're very close to each other. They start to differ at this digit. And of course, this example is where exact answer is already known, which takes this form. And this is, of course, in between these two values. But here, I wish to highlight one very important conceptual point, which is that this minimum and maximum are actually rigorous lower and upper bounds on the exact answer. Why is that the case? These bounds are rigorous because we impose what must be true, okay? In all of these conditions, we didn't take any approximation. We are not doing any perturbation theory. We are just imposing what must be true. Okay? So the corresponding results must be rigorous. And this is the very philosophy of Bootstrap. Bootstrap philosophy is that you want to impose whatever that should be true for your theoretical system, and then you explore what the consequences are. And in this case, one can actually come up with a proof that as you increase the cutoff, lower and upper bounds are actually going to converge to each other exponentially fast. Okay. So far, so good. Okay. So let's take a step back and reflect on what we actually did. We were essentially considering this path integral. And this path integral consists of two parts. First part is sum over all configurations. By configuration, what I mean is the different real values that x can take. And each different value of x are now weighted by this vector. So basically what we are doing is that in this toy example, we are bootstrapping some notion of ensemble. we are considering all possible configurations with some weight, and we have been bootstrapping such an ensemble. Now we can imagine how to extend such an analysis to more general cases, and today my goal is to tell you about how to bootstrap using very similar idea, the thermal ensembles, which is basically the physics at finite temperature. I'm going to mainly discuss two examples today. First example is statistical Ising model on the lattice. This is the good old Ising model on the lattice that we all learn in STEM Mac course. And the second one is large M matrix quantum mechanics.
Can I
let
ask
me,
one?
sure.
Yeah, in user, I'm little familiar with the conformal bootstrap or asymmetric bootstrap in integrability. In those cases, the bootstrap is the tightly related to some symmetry, right?
That is
So
right.
here, bootstrap in thermal things, then what is the symmetry in thermal system? Can
Great.
you help that?
So yeah, so the reason why symmetry arose in conformal bootstrap, for example, is because it is, in a sense, one must be true for in any systems at conformality or criticality. Okay, that's the reason why. Yeah. So in this sense, I would like to tell you that the general philosophy of bootstrap, in general, do not actually require notion of symmetry. It's just that once you want to bootstrap a specific system, and if that system happens to have a lot of symmetry, just like in conformal field theory, then actually you can impose them, and they're going to help you bootstrapping the system. But in this case, actually, that's exactly the point. Like, there are physical quantities which are not just dictated by symmetry and which are not constrained enough by symmetry. And the power of bootstrap exactly lies in the fact that bootstrap philosophy still goes through, and it can actually determine many of the quantities which are not dictated by symmetry alone. And actually, so here we talked about positivity. This is actually one of the essential ingredients of the modern, say, numerical conformal bootstrap. In the numerical conformal bootstrap case, the corresponding positivity is actually reflection positivity. And that actually leads to, say, the reality of the OP coefficients. And you can find the SNT channel where you can write down the basically semi-definite programming constraint for such a crossing equation. Yeah.
Thank you.
Thank you very much for the question. Any other questions? Okay. So before jumping into the explicit example, I want to give you some broad picture about thermal ensemble. So we are going to consider some space of states or configurations. And there's also going to be notion of either Hamiltonian or energy. And by thermal ensemble, we mean that we have ensemble of states, but they're weighted by a factor e to the minus beta a. Here, this beta is the usual inverse temperature. Well, the point about finite temperature is that every state, in principle, contributes at finite temperature. This is in much contrast with zero temperature, where only the lowest energy states matter. So naively, if you just look at this type of definition, it might sound very difficult because it actually seems to require enumerating all possible states and their energy. Turns out that exactly for this reason, historically, people have came up with alternative formulations which are practically more useful. And today we are going to see which of those alternative formulations actually help us do the bootstrap. So finally, we are at our first example, which is statistical Ising model. I think everyone is familiar with this, but let me still give the brief intro to the system. So let's first start with the finite lattice. We are going to have some finite lattice in the integral lattice. So this is d equals 2 case, two-dimensional, 3 by 3 lattice. And at each lattice site, we are going to assign spin. This SI is the usual spin variable, which can take values plus or minus 1. Of course, the total state space is then given by the power set of this plus minus 1. It means all possible plus minus 1 assignments over every site in your lattice. In this context, what we mean by thermal state is something called Gibbs measure. Okay? And that's defined by this partition function. So we are again summing over all states in the state space, but together with this wave vector. And this W you can interpret as minus beta H. And this is the familiar form of the Ising Hamiltonian. Okay. So we have sum over nearest neighbor pairs. This is sum over nearest neighbor pairs. So this is nearest neighbor interaction term. And this is the external magnetic field term. Okay. Of course, if you are on a finite lattice, then you can compute this partition function explicitly. And your expectation value of any function of the spin configuration is given by this expression. Okay. This is over normalization stuff. And then you are going to weigh each state by this weighting factor, and then together with your function insertion. Well, so what is the problem? The problem is exactly that this sum, if you want to actually explicit sum over all possible spin configurations, it becomes exponentially expensive as the size of the lattice grows. So what makes it even worse is the following. Now let's consider infinite lattice case. Okay. Actually, this is where interesting physics happens. For example, phase transition. Phase transition takes place only on the infinite lattice. It cannot take place on finite lattice because any finite sum is going to have analytic expression. So there is even a fundamental question about how do we even define the Gibbs measure once we are on the infinite lattice, because we cannot sum over all these infinite stars. This is exactly where Dobrshin, Lamford, and Rule in 60s came up with alternative definition of the Ising model on the infinite lattice. And their idea was based on something called conditional probability. So the insight they had was the following. Ising model had, as you can see here, just the nearest neighbor interaction term. Okay, so in a sense, there is notion of locality. And based on this locality, you can ask the following question. Say you are interested in some site I. Okay? And now consider all of its nearest neighbors, J. And say you have specific spin assignments, let me call them uj over them, and given such nearest neighbor spin configurations, now what is the probability that the central spin takes value ui? Okay, so condition on the nearest neighbor spin assignments was the condition of having the spin assignment at the central location to be ui. That is the conditional probability of our concern. And what DLR observed was that for all those finite lattice cases, this is the expression. This is the answer. And moreover, just requiring that your measure satisfies this conditional probability actually completely determines your entire partition function on the finite lattice case. So this is equivalent definition of the Ising model. Okay. And then DLR had idea that, okay, this holds true for finite lattice case. We just declare that Gibbs measure on the infinite lattice is simply any measure which satisfies this conditional probability. This makes sense because Ising model has locality. It only has nearest neighbor interactions. So this is the mathematically rigorous definition for Ising model on the infinite lattice. Of course, mathematicians would always like to ask questions about existence or uniqueness. They proved existence. And the answer to uniqueness actually depends on your choice of the temperature and the external magnetic field. For example, if you turn off your external magnetic field, then there's low temperature and high temperature region. And it turns out that you can have either unique answer to this question, or you can have infinitely many answers. Okay? And the transition point between these two is exactly where the phase transition happens. So now let me ask the following
is
question.
there some just not so much relevant, but is there long-range generalization beyond this nearest neighbor for DLR?
Oh, yes.
It's conditional
So
probability.
as long as you just assume that the range of the interaction is finite, you can still come up with very similar type of conditional probability statement. Indeed. Yeah. Good. So now let me ask the following question. Okay. I mean, in our toy example, toy example was also about basically bootstrapping a measure given some conditions. Okay, so now we can ask the same question. We have Ising model, which is described by a positive measure, which should satisfy some conditions. And those conditions are exactly this conditional probability statement. Now the question is, how do we teach? Okay, how do we teach our computers about this constraint? Because computer can only understand variables or number. Okay. Well, in order to do that, let's try to express everything in terms of expectations. If you recall the toy example, that's exactly what we did. We expressed Schwinger-Dyson equation as a linear relation between expectation values. So let's try to do the same thing here. In order to do that, consider this function. This is 1 plus si over 2. And of course, this is 1 if your spin is 1. It's 0 otherwise. Okay. And this type of function is something called indicator function. It really indicates whether your spin at I takes value 1 or not. And because of that, if you take the expectation value, it has the interpretation that it's the probability that your spin is going to take value plus 1. Okay? Well, given this, now we can rephrase DLR equation. So it was conditional probability. So here, this is the indicator function indicating that your nearest neighbors takes spin assignments uj. Okay, now conditioned on this, what's the probability that you further have si being ui? Okay, so this expression is exactly the conditional probability that DLR considered. Now expressed in terms of the expectations. And the right-hand side, given any spin assignments, is simply a number. And now the problem is basically the same as the toy example that we saw before. So in the toy example of phi-4 theory in 0 plus 0 dimension, we had linear relation between the expectations. We again have, upon moving this thing to the right-hand side, we again have linear constraints among polynomial moments. Okay. So now we can repeat the same exercise as before. So what are the conditions? We have positivity, which is simply saying that we have a positive measure. So expectation value of any indicator function has the interpretation of probability, so it better be positive. Okay, this is the manifestation of the fact that we have a positive measure. And DLR equation was basically linear equations among this type of expressions. Okay, and then you can impose some, some usual stuffs. Say 1 is normalized 1, and its spin squared is equal to 1 because it can take only values plus minus 1. And you can impose symmetry if you want, such as translation, rotation, and reflection. And all of these are linear constraints on the expectations. So we ask exactly the same question as before, okay? Subject to all these constraints, we want to either maximize or minimize some correlator of interest. Okay, that is our question. Turns out that this is something called linear programming, in short LP. This is the definition of linear programming. Here, xi's are the variables, while a, b, and c are some constants, okay, given constants. And that's exactly the form of this problem. And once you do this business, you're going to obtain minimum and maximum, and again, those are going to provide rigorous bounds on the exact answer. Just like our toy example that we discussed before. So here are some results, very preliminary results. So in D equal 2, you can take this J value. Actually, this is the criticality value where the phase transition happens. And you can turn off the magnetic field. This is the nearest neighbor correlator, and the exact answer is known to be this number. Okay? Now, what about the bootstrap approach? In the bootstrap approach, we are doing linear programming, but of course, we cannot impose infinitely many constraints, so we are going to only impose some subset of these infinitely many constraints. And for that purpose, we are going to consider this subset of lattice inside the infinite lattice, okay? And we are going to consider all possible spin insertions within this domain, okay, within this diamond. And if you run this thing on your computer, just like the toy example, you are going to obtain these two rigorous bounds. These are not yet quite tight, but soon I'm going to give you very tight answers. Okay. But good thing is that this is actually consistent with this exact answer being in the middle. Okay. I mean, of course, one can ask just mathematically. If you consider, bigger and bigger and bigger domain and, more and more constraints, do you actually get a convergent result? And that's what we proved in our paper. Basically, as you increase the size of this diamond, your minimum, for example, or maximum, is going to converge to actual value of the Gibbs measure. Well, let me emphasize the following. Even though you are imposing these constraints within this finite region, the bounds you obtain are still rigorous for the infinite lattice. It's just because we have definition for infinite lattice measure, and we are just imposing some finitely many subset of that. Okay, but we are still imposing whatever is part of the definition. Okay, that's the reason why these numbers provide rigorous bounds on the infinite lattice case. Well, this type of theorem has very important philosophical implication, which is that Bootstrap actually provides a very practical definition of the system. Now let's try doing a bit better. You can actually add further bootstrap conditions. Okay, even though the previous conditions were already enough to guarantee the convergence, you can still get better bounds at each step if you impose more conditions. And for example, there is a very well-known positivity called reflection positivity, which is obeyed by Ising model. And all that this is saying is that if you have reflection symmetric spin configuration, and if you take the expectation value, the corresponding expectation value is going to be positive. That's all it's saying. So here we can consider generic expression, linear combination of some spin configurations on the half space. Let's say if we are considering this R1, this hypersurface, we can consider any spin configuration here. And then you can define the reflected one, okay? So you can have the same thing, but reflected on the other side. And now reflection positivity amounts to this positivity. Okay? And after a short computation, you can see that this is actually equivalent to positivity of some matrix, where the matrix elements are defined in this manner. Okay. I'm skipping some of the details, but essentially all I'm saying is that reflection positivity can be expressed as matrix positivity in terms of the expectation values. Okay.
I have just one quick question.
Yep.
So when you say positivity of the matrix, do you mean the positivity of each element or?
No, it means that, so these are, for example, real symmetric matrix, so you can diagonalize it, and the
Positive
eigenvalues are
eigenvalues.
positive.
Okay, thanks.
Thank you. Thank you for the question. So, this matrix positivity is something that we already discussed in the toy example, the very first example. And this type of problem is called semi-definite programming, SDP. Okay. So we can run all of this thing on a computer. And here are results. So let's first check the cases where we know the analytic answers. So this is d equals 2 at 0 external magnetic field. We are going to use reflection positivity together with DLR equation. And these are the bounds on nearest neighbor correlators. Okay? These gray dots are coming from D2. Basically, we are imposing only this tiny set of constraints. And these blue dots are the upper and lower bounds obtained by D3. And you can see that it converges pretty quickly. And this blue region is where the allowed region, where the exact answer should lie. And this black curve is the exact answer. We can also consider the magnetization. Okay. As we are familiar with, so this J is inverse temperature. Basically, in low temperature region, which is this region, there's a spontaneous magnetization. And this is the analytically known answer, while the bootstrap upper bounds are given by this thing from D2 and this thing from D3. So you again see that it quickly converges to the known answer. Of course, the fun starts when we consider the example where there are no known analytic solution. Okay. So even in 2D, as soon as you turn on the external magnetic field, there's actually nothing known. analytically. But Bootstrap is still there. You can just implement the exactly same thing as before. And this is the bound on the nearest neighbor correlators as a function of external magnetic field and the inverse temperature. The color sheet on the top is upper bound, and this grid on the bottom is the lower bound. But they become almost indistinguishable, and that's the reason why we actually colored the plot. So here the color, what color represents is the difference between upper and lower bound, okay? And it's in logarithmic scale. For example, here are yellow region, and yellow corresponds to roughly 10 to the minus 6. This blue region, for example, is where the difference between upper and lower bounds are 10 to the minus 15 or smaller. Okay? So in this blue region, for example, you can say that Bootstrap determines this nearest neighbor correlator to 15th digit. And this is by far the most precise and accurate numbers that you can find about statistical Ising model on the lattice in literature. Okay? And of course, there's another interesting case of 3D. Even in the absence of external magnetic field, 3D case still is not solved analytically, but Bootstrap is Bootstrap. We can impose upper lower bounds. Those are given by this. And this red line is the result of some Monte Carlo simulation. Any question before I jump to the next example?
I have just one quick question. So the convergence theorem you proved, I guess that's for h equals 0, right? No?
Oh, no, it actually holds for any h and any j.
Oh, so you mean that even for the case where there's no known analytic method, you know that upper and lower bound should match in the angles?
Yes.
Oh, that's interesting. I see. Thanks.
That's right. Yeah. Thank you very much for the question. Yeah. So that's the reason why I want to emphasize that Bootstrap serves as an alternative definition of the Ising model. Okay. That's why such convergence theorem is very meaningful. Okay, now let's jump to the next example, which is quantum mechanics at finite temperature. Okay. We start with some quantum mechanical system with Hilbert space curly h and Hamiltonian big H. And by thermal system, what we mean is we have thermal density matrix, which takes this form, e to the minus beta h. We are going to assume that it's normalized correctly. Of course, here I am assuming that it's trace class, but don't worry too much about the formality. Later, I'm going to present you the explicit definition, which applies both for infinite dimensional and finite dimensional Hilbert space. And given such density matrix, we can define the expectation value of any operator given by this trace expression. Okay. Well, up to this point, it's just definition of thermal density matrix, and it actually satisfies the celebrated KMS condition. And in turn, you can also show the KMS condition is basically the defining property of this thermal density matrix. Okay. What it's saying is that given any operator O1 and O2, you can consider this type of correlator. That's actually the same as this expression. Okay. This is a celebrated KMS condition. And in particular, if you consider O2, for example, O1 being Hamiltonian itself, this thing becomes usual Schrödinger-Dyson equation. This is just saying that thermal state is a stationary state. Okay. Well, so here you might say, okay, we know that density matrix should have some positivity. And also KMS condition itself is linear in the expectation values. So you might say, okay, we can apply the bootstrap again. Well, that's a bit too quick. The reason is because this KMS condition is actually hard to implement in practice because we have exponentiated operator. So for example, if you consider this in Ising spin chain, now this type of expression can grow uncontrollably and you have non-local expression. Okay. So the question is, how do we come up with some equivalent formulation of this type of condition in a manner that we can actually implement it on the computer? Okay. Well, I am not the one who solved this problem. Turns out that this problem was solved already in the 70s by very famous math physicists, Araki and Sewell. And it has been recently revisited by these friends in the optimization community. So this is a paper which is less than a year ago, which was published less than a year ago. There is actually a behind story. So when I wrote the statistical Ising bootstrap paper, I sent the draft to this guy, Hamza Fauzi. He's my talk-to person in optimization community whenever I work on some optimization problem. And that thing motivated him and his collaborators to consider the quantum extension of my work on the statistical Ising model. And basically, this is what they show. So KMS condition, which is basically the defining property of the thermal state, is equivalent to following condition, which I'm going to call FFS condition, following this guy. So first, we have to impose Schwinger-Dyson equation. So far, so good. This is what we already know how to deal with. And second part is the non-trivial one. I'm going to call it thermal inequalities. Okay. It actually consists of three matrices, A, B, and C. Okay. Here, OIs is some basis of operators. And this is A matrix, this is B matrix, and this is C matrix. Okay. A matrix is the usual positivity matrix that one can consider. B matrix is some, different version of it. C matrix involves perturbation on the energy, as you can see here. Okay. So given these matrices, this inequality should be true for any thermal state. And this is, again, defining property of the thermal state. Okay. And you impose, again, positivity of the thermal density matrix, which is saying that this type of expression, whatever O, should be positive. Well, if you want some intuitive understanding of this thing, you can notice that this is kind of like, this C matrix, this term, is like the energy perturbation. While this log type expression, in STEM or quantum mechanics, the only place where we typically see log is when we discuss things like entropy, right? So this is roughly like, energy minus temperature times entropy, which is nothing but the expression for the free energy. So there's actually equivalent formulation of the KMS condition in terms of minimizer of the free energy. And actually, this is how that thing arose in Sewell's paper in 77. So what did we obtain? Well, we are still not quite there yet. It's because Schwinger-Dyson equation is linear, so that's good. Positivity is linear in all these things. These matrix elements are all linear in the expectation, so we are good. This thing, okay, we got rid of the problem of non-locality. All these expressions are local, okay? If we assume that all these operators are local. But the problem is that this inequality is not quite linear. Okay, it actually involves log. So now we have to do extra work. Well, I didn't do the extra work. These guys did the extra work. These guys in the optimization community. So basically what they considered was like the following. So log, let's consider the usual log of x. This is just one real variable. It has integral representation, okay, where this f of t has this expression. The upshot is that if you consider this type of inequality, it's equivalent to positive semi-definiteness of this 2x2 matrix. Okay, so even though log is very hard to express in terms of all these inequalities, this integral is very easy to express in this type of SDP constraint. Okay, so that was their idea. So we have integral. Now let's just approximate it as some Riemannian sum. Okay, so you can consider some Riemannian sum. These TJs are basically discretizing the interval between 0 and 1. And these W's are some weight. Okay. And there are some typical ways to do this type of discretization, Riemannian sum for the integral. And you can discuss how well it converges and so on. The one which I'm going to use is something called left Gauss-Radau quadrature. Okay. Don't worry too much about the details. It's just one possible way to approximate the log or this integral in terms of finite sum. Okay. But it has key properties. First is that as you increase this n, which is basically the number of points that you are dividing the interval into, it actually can approximate log of x at any given x arbitrarily good. Okay, so it converges as you increase n to infinity. Second essential property is this one. Okay, log of x is always smaller or equal to this approximation. Okay, so even though we are going to take approximation for the logarithmic expression, we are not going to lose the rigor of the bootstrap. Okay, because we are going to have approximation which is strictly bounded. One can do further improvement. Actually, this approximation is always exactly true at x equals to 1. So if you can somehow bring the points closer to 1, you can get better approximations. So this is my final form of the approximation for log. Okay, it's labeled by two natural numbers m and k. K is how much you are bringing the points closer to x equals to 1, and m is the number of the divisions that you make for the interval. And because of this strict inequality, what you can show is that the original thermal inequality, okay, the original thermal inequality, which takes this log form, actually implies this RTI, relaxed thermal inequality, where you replace log by this expression. So what's the direction of things? The direction is that KMS condition is equivalent to this thermal inequality, but this thing implies this relaxed condition. So as long as we are probing this relaxed condition and we find some bounds within this condition, that's still going to provide rigorous bounds on the actual thermal expectation values. That's the idea. Okay, we are relaxing the problem, and because we are strictly relaxing the problem, we still obtain rigorous bounds. Okay, that's what we are doing. And basically, because this expression, we call that this function. This expression was all about this function, which has this SDP representation. For that reason, this RTI condition can be equivalently formulated as some SDP constraint. And here's the theorem proven in this optimization paper. All it's saying is that this is equivalent to existence of Hermitian matrices T's and Z's, such that one of them is B, somehow some weight plus times this TJ matrices sums up to this C matrix that we considered before. And then we have to impose these block matrices to be positive. Okay. And A matrix appears here. So now this is something that we can plug into computer. So let me give you a summary. So this quantum mechanics thermal bootstrap is, again, SDP problem. Okay. So we are going to maximize or minimize some operator thermal expectation value of interest subject to these constraints. First, Schwinger-Dyson equation. This is linear. And then we relax thermal inequality. This is SDP. And we also have positivity. This is again SDP. And normalization. And if you have further operator relations, such as canonical commutation, you can further impose that. And they will give rise to linear equations. And this is something just like the toy example that we considered at the very beginning. This is, to a computer, this is not different at all. Okay. It's just exactly the same problem to a computer. So you can put it into computer, it's going to produce minimum and maximum. And again, they provide rigorous bounds on the exact answer. So FFS, in their paper less than a year ago, applied this thing to quantum Ising spin chain, and they obtained very nice bound. Okay. Well, our interest was in large N matrix quantum mechanics. So we decided to start with 1x1 matrix case, okay, which is basically single particle. So consider this single particle Hamiltonian. And now we basically run all of these, optimization problem, this bootstrap problem. Once we do that, we are going to obtain upper lower bounds. And the thing which we considered was the Hamiltonian expectation value. You can consider this as the derivative of the free energy. Now, this thing as a function of t is plotted here. So here, this 2,2, 3,3, and 4,4 stand for this approximation scheme, m, k. And as they increase, we get better and better bounds. Turns out that 3,3 and 4,4 are hardly distinguishable. So actually this blue curve is lying behind this red curve. Okay, and as you can see, the bounds are converging pretty nicely, and it's pretty tight here. Okay, so it almost determines the value. And this black solid line is the one which we obtained by literally solving for the first 10 excited states of this thing, and then considering their contribution to the thermal partition function. And they are in very nice agreement. So this was a simple test case, and it works very well in this test case. So now we want to consider matrix quantum mechanics. So we are going to consider something called ungauged large N matrix quantum mechanics at finite t. So there are several keywords here. First of all, what do we mean by matrix quantum mechanics? The fundamental degrees of freedom in these systems are n by n matrices. Just like in any n by n matrix model, there exists hooped large N expansion, which takes the form of genus expansion. And we are going to be concerned with the planar physics, meaning that we are going to be looking at only the leading order in the hooped limit. Well, why are these interesting? Because these are expected to be dual to some gravity or string theories. And there's this phenomenal example of C equals 1 string theory. Now, what's special about finite temperature states in matrix quantum mechanics? They're expected to be dual to thermal backgrounds on the dual side, which in particular may correspond to black holes. Well, this type of bootstrap idea has already been applied to stationary states in these works. Note that it dates all the way back to Polchinski, 99. This is actually the paper where Polchinski tries to explain the connection between M theory, digital brain, matrix quantum mechanics, BFSS, and type 2A, and various things. And in the end, he actually writes down how to measure the size of the wave function using bootstrap technique, even though he didn't call it bootstrap. And these are the papers where further systematic investigations have been performed. Well, now what we can do is that we can employ this FFS framework and now bootstrap this system at finite temperature. So this is the example that we are going to be concerned with. This is one matrix quantum mechanics. So this X and P are n by n traceless Hermitian matrices obeying the usual canonical commutation relation. This A and B indices range from 1 to n. So X and P transform in the Asian representation if you wish. Note that we have this G. Okay, this G is basically the coupling for the quartic potential, and we are going to play around with this G later. Because the Hamiltonian takes the trace form, there is global UN symmetry, which is basically the adjoint action by any unitary matrix on your X. There are two notions of this matrix quantum mechanics that you can find in literature. First is the gauged matrix quantum mechanics. This just means that you are going to restrict the Hilbert space to the singlets only, singlets under this UN. And in this case, there's a very well-known story of non-interacting fermions at large N. And this is the thing which people typically solve using various methods. There's also something called ungauged matrix quantum mechanics. Okay? Basically, what it's saying is that you just do not make any restriction, and you have to consider all the representations, which is coming from products of adjoints. Okay? This problem is actually way more non-trivial than the gauged case, because now the non-interacting fermion picture is no longer available in generic representation. For example, if you are familiar with the C equals 1 matrix model, the adjoint sector is actually dual to the long strings on the C equals 1 string theory. And those are very difficult thing to study. In particular, if you now consider finite temperature, you have to basically take into account contributions in principle coming from all these representations. And it sounds like a very difficult problem to discuss. Of course, if you're in low temperature or high temperature region, there are some productive expansions that you can take. But if you want to study something in the genuinely strong coupling intermediate temperature region, that's where none of the analytical methods are currently developed. But good thing is that bootstrap is bootstrap, you can still impose Bootstrap. So this is the setup. We are going to consider operator basis, which is basically words consisting of X and P. And generically, we are going to be considering this type of thermal correlator, thermal expectation value. And this A, B, and C, D indices, which are ranging from 1 to n, allows for SUN invariant tensor decomposition. The option of this group theory exercise is just to say that all these expectation values, these operators carrying all these indices, actually reduce to just expectation values of the multi-traces. Okay. The positivity that we are going to consider is this one, is trace of Odega O being positive. Now we can consider reduced thermal inequality. We are going to consider specifically 1-2-1 matrix element here. Okay. It turns out that this is the only non-trivial thing that you can consider at the leading order in large n. And that expression gives rise to both single trace expectation and double trace expectation. And you can do the similar thing for B and C matrices. And you impose the other things as usual. Schwinger-Dyson equation. You can impose trace cyclicity, canonical commutation, and reality. Okay? These are the constraints which should be satisfied. And they actually provide linear relations among single trace and double trace expectations. One comment is that typically in large n, multi-traces actually factorize into products of single traces. In this case, we are not going to take that factorization because then the problem is no longer linear. Instead, what happens is that once you actually solve for all these constraints, for example, if you consider operators up to word length 10, there are, for example, only 3 independent double traces left over. And we are simply going to treat them as just independent variables rather than single trace squared. Of course, one can take it as single trace squared. There is a strategy of tackling such a problem in convex optimization called relaxation, quadratic relaxation. But for simplicity of implementation, we didn't consider that. Anyway, this is the setup. We can just plug this into the computer, and these are the results. So at infinite n, this energy expectation is of order n squared. So we are going to be interested in the coefficient multiplying that. And we are plotting it at different quadratic coupling values. We are putting the upper and lower bounds as a function of temperature. So this is considering words up to length 6, 8, and 10 respectively. And as you can see, the bounds converge very quickly. Actually, for all of these plots, you can hardly distinguish the upper and lower bounds coming from these green lines. Okay. In the low temperature region, for example, the difference between upper and lower bounds are like 10 to the minus 8. In particular, we can make comparison against low temperature or high temperature expansion. So in the low temperature expansion, we know that the first term is given by the constant ground state energy. And the leading order correction to this one is coming from the edge-joint gap. Actually, solving for this edge-joint gap is a very non-trivial problem. It's first discussed in this paper. And this is also known as long string wave function equation. It takes the form of singular integral equation, and you can solve it, and you can obtain this thing. You can also consider high temperature. This one is obtained by considering the Euclidean path integral on a thermal circle. This is a usual thing where if you now consider the thermal circle, you can do the free expansion, and non-zero modes carry thermal mass. And those masses actually are very high in high temperature. And for that reason, in the high temperature limit, this path integral actually reduces to the ordinary 0 plus 0 dimensional matrix integral. And using that, this is the answer you can get. So this is very strong coupling. And you can plot upper and lower bounds from the bootstrap. That's actually this yellow line, okay? We also plotted upper bound, but it was simply indistinguishable by eyes from this lower bound plotted here. This blue is the low temperature expansion, and this green dotted line, gray dotted line is the high temperature expansion. And as you can see, in all this intermediate temperature regime, there is a huge deviation between the bootstrap result and all these analytic results. Okay. This is basically demonstrating how non-trivial bootstrap results are in this intermediate temperature region. There's another very interesting thing you can consider, which is to take the value of the quadratic coupling to be negative. Okay, so your potential is going to look like this now. It's unbounded potential. And in any quantum mechanical system, you might say that, okay, it cannot have any finite energy state because of tunneling effect. Even if you have localized wave function here initially, it's going to leak out due to quantum tunneling. But what happens at large n in the Hooft limit is that large n actually suppresses such quantum tunneling effects. And for that reason, as long as you are not too negative, your G value is not too negative, and it's bigger than this critical value, there actually exists finite energy ground state. Okay? It doesn't leak out to the outside of the well. So now we can ask the question, okay, in this region where you have finite energy ground state, even though you have unbounded potential, you can ask what happens if you try to boil the system, if you put it on a finite temperature. Can a thermal state of some specific temperature exist? The rough picture is like the following. If you now boil this system, some of these energies, some of these building levels want to now jump outside of the well. And once that jump actually happens, your state is no longer going to be stable. And your thermal state cannot exist. The answer is like the following. Given a specific value of G in this region, there exists critical temperature such that thermal state exists only if your temperature is below this critical temperature. So the question is, how does Bootstrap find such a thing? Well, say we are given some coupling. You can run SDP. SDP is based on some constraints that we impose. These are like thermal inequalities, Schwinger-Dyson equation, all of those things. And recall that those are nothing but something that comes from the definition of the thermal state. Okay? So if somehow your computer finds that these constraints are infeasible, meaning that they contradict each other, it means that your thermal state cannot exist. And for that reason, if you actually have your computer finding such infeasibility at some temperature T, say T of SDP, then it actually is going to provide a rigorous upper bound on this critical temperature. So here are results. The critical temperature is something like minus 0.0751 da da da. And here we have upper and lower bounds. This upper bound, lower bound, upper bound, and lower bound, together with low temperature expansion. And this red line is where SDP finds bootstrap constraints infeasible, meaning that there's no thermal state above this temperature. And you can collect this infeasibility certificate and plot this critical temperature or the upper bound on the critical temperature as a function of G. And this is the result. And this red line is the critical value of the coupling, where the critical temperature is expected to be 0. And you have this very nice upper bound. And let me emphasize again that this type of critical temperature is something that we currently do not know how to analytically study. But Bootstrap is Bootstrap. It provides very nice upper bound on this critical temperature. So let me come to the discussion part. So hopefully the main message is clear, which is that Bootstrap is a natural framework for thermal physics. Why is that the case? Because finite temperature states are just by definition, they are defined by convex conditions on the expectation value. And this type of convex condition, you can teach your computers. Okay? And they typically take the form of linear programming or semi-definite programming formulation. And your computer is going to produce some numbers which can be interpreted as rigorous bound. And sometimes they are very precise, and there are even convergence proofs. Now, specifically about the examples that we discussed today, statistical Ising bootstrap relied on locality. Okay? And because of this, it is still computationally expensive to study long-range correlators using bootstrap technique. So now one can ask, is there a way to tackle this type of long-range correlators more directly? Okay, is there some reformulation of the system in a way that these are better studied? There's also interesting contrast between positivity of the measure and reflection positivity. Typically in Euclidean quantum field theory, we take reflection positivity as the God-given positivity. Okay, this is one of the most essential property of QFTs. But today we saw that from bootstrap perspective, for the conversions, all you really needed was just the positivity of the measure. You didn't even need reflection positivity. So there is an intricate contrast between the two. You can also ask about the relation to Monte Carlo simulation, which is another very well-adopted way to study thermal systems. Actually, there is a very nice relation between Bootstrap and Monte Carlo. I refer you to this paper. The main idea is that Monte Carlo is just a stochastic process, and you can study its invariant measures. And you can actually bootstrap such invariant measures. Today we discussed ungauged large and matrix quantum mechanics. There's a closely related one, which is gauged large and quantum mechanics. And we can hope that Bootstrap can again produce important results on this case. And also, let me tell you that there exists very interesting finite temperature phase transition in large and matrix quantum mechanics. For example, you can refer to this paper, and we can ask if Bootstrap can see this type of phase transitions. And finally, there's also interesting case of BFSS, matrix quantum mechanics, which is due to N theory. So studying finite temperature properties of this theory will tell us about the black holes on the field side. And let me end with this very broad picture. So the only ingredients for the bootstrap was positivity and some convex equalities. Okay. Now you might say, okay, what if I have some completely different type of setup, but still having this type of ingredients? Then you can actually impose bootstrap. So this is the reason why this type of approach has been applied in various setups. Actually, the very first example where this idea has had a major success was in the 90s in the field of quantum chemistry. And this has been also applied in applied mathematics, optimization, and so on, in studying discrete or continuous dynamical systems or stochastic processes. And in our field, there are also other lists of applications of bootstrap, such as lattice gauge theory and conformal bootstrap or asymmetric bootstrap that was already discussed. So here's a comment, which is that just think about the problem that you are currently trying to solve and see if it has this type of components. If that's the case, then you might have a chance to apply bootstrap to your problem. With that, I wish to end my presentation and thank you very much for your attention.
Thank you. Thank you so much. Questions? Yeah. Any questions? First, I have question. So you already mentioned the Hagedorn and deconfined paper by Minala.
That's right.
So you mean basically by using your very natural framework for thermal physics, can you also study some black hole entropy and some small black hole, large ADS black hole, also other?
Right. That was actually one of the very motivations of this project. So our motivation was to see if we can actually study the thermodynamics of these black holes on the dual side, basically matrix quantum mechanics side. We are not there yet. We just studied the very simplest setup, but hopefully we can continue our project to such more interesting cases. And yeah, hopefully in the end, this is one of our big goals, BFSS, matrix quantum mechanics. Yeah. But I mean, if you look at this paper, for example, there's a very simple toy example, which manifests this type of Hagedorn phase transition, which is
Exactly.
you can
Just
consider
two metrics, right?
exactly two free matrices which are
Yeah.
not interacting with each other, but the only thing they are interacting with each other is via gauge singlet constraint.
Exactly.
And in this case, they came up with this unitary matrix model, which is the way to see how this state transition happens. So that will be a very nice quick example that one can target at, and we can hope to actually see whether we get an agreement with the result or not. Once we get the agreement with such a simple example, I think then we can expect that the Bootstrap framework is then going to have non-trivial results also on the other more interesting examples. Yeah. Thank you very much
also
for the
the
question.
Dyuta-Kopakuma's matrix model that is also related to that. Yeah.
That is right. That is right. Yeah.
I see.
There are actually many interesting matrix quantum mechanics
Of
that one can hope
course,
to study. Yeah.
Okay, thank you. Yeah. Please,
Thank you very much.
any other questions? Yeah.
I have questions. Yeah. Thank you for your talk, both.
Thank you.
I want to ask you about this, what you call DLR formula or expression.
Let me go to that slide. Yes, here it is.
Yeah. First of all, is this essentially a familiar Fermi-Dirac distribution? You have either 0 or 1 spin value, and it looks like you are obtaining Fermi-Dirac distribution here.
I will say the expression is looking very familiar with Fermi-Dirac distribution, but the interpretation here is simply that of conditional probability. So
I mean, Fermi-Dirac distribution is also probability. It's correctly normalized.
That's right.
Yeah.
That's right. So it's a probability once you're given some temperature of some specific energy states being occupied, right?
Yeah.
This one is a bit different. It's literally just a conditional probability statement about the specific, if you have specific assignments of nearest neighbors, what's the probability that your central spin assignment is given by specific spin?
I mean, presumably,
conceptually they are different.
Yeah. I mean, but presumably they derive this result by maximizing some total number of cases or something like the total number of possibilities. And I imagine
there may be such an interpretation, but at least I'm not familiar with such an interpretation.
Okay, so and then actually I was a bit caught with this formula, and I somehow missed how you impose this DLR formula into your Bootstrap. I mean, I missed that part.
Right.
Could you say about that? Yeah.
Sounds great. Sounds great. Oh, thanks for the question. So maybe I was too quick there. So this conditional probability can be expressed in terms of expectation values. So if you recall, in the Bootstrap, we want to express everything in terms of expectation values.
Mm-hmm.
So now the question is, how do we express this type of conditional probability in terms of expectation values? And the answer is this. So what is this? Below here is indicator function, which is indicating the specific spin assignment of your nearest neighbor. And the corresponding expectation has an interpretation of the corresponding probability. So given this nearest neighbor interaction, nearest neighbor spin assignments, what is the probability that on top of this, your central spin takes specific value ui?
Okay,
so this is, and then now these are the variables which we can plug into computer, and computer will happily solve this for us.
And you impose this relation all the way in your computation.
That's right.
Thank you. Yeah.
Thank you.
For the
oh, I see. I see a message.
There's a message from Sanghan Lee.
Yeah. Determining the potential Hamiltonian from given data. Oh, very good question. Honestly, I have never thought about this direction. Very good question. Yeah. Actually, yeah, this also sounds like an optimization problem. Given some data, what is the optimal parameters that's going to be closest to the data. I think there gotta be a way to phrase that. And yeah, actually, I mean, this is pretty orthogonal, but there are actually applied mathematicians studying this type of inverse program. The most well-known example is actually visualization data. If you are familiar with it, if you have some, say, MRI scan or things like that, these optimization people have some way to, grasp those data and extract some important, functions out of it. So I guess that's the related thing, but it's something that I have never worked on personally. But very good question. Thank you.
For the question or messages, so from student, no? Okay, so if there is no question, then please let's thank again 민재.
Thank you very much. I really appreciate it.
감사합니다.
Thanks for your talk.
감사합니다.